Hi, my name is Nick, and today I am going to present our paper entitled Leveraging Synthetic Subject Invariant EEG Signals for Zero Calibration BCI. In this work, we use SSVEP-based EEG signals for BCI application. SSVEP, or Steady-State Visual Evoked Potential, is a type of neurophysiological response induced directly via subject fixation on a frequency-based visual stimuli. However, the acquired signals are often heavily subject and session dependent that leads to long and tedious calibration requirements, especially on cross-subject generalization. This figure shows our real-time BCI application workflow with calibration stage shows in red dotted rectangle. These subject dependence attributes of the signals caused by the unique patterns existed in the signals to specific subject, where EEG signals can also be used as a biometric. This makes the collected EEG signals incapable of accurate generalization on new previously unseen subject, which leads to the requirement of calibration stage for any application, thus restricts real-world practical applications. In this paper, we exploit the capabilities of a subject-invariant SSVEP generative adversarial network, SysGAN, to produce not only realistic synthetic EEG signals, but also to eliminate subject-specific features in order to boost performance on subsequent tasks. The SysGAN model architecture comprises four primary components: a generator network and its corresponding discriminator, an auxiliary classification network, and a pre-trained subject biometric classifier. We design our training process in such a manner that the network is rewarded when it learns features that are common across all subjects and is penalized when subject-specific features can lead to subject biometric classification. To achieve this, we introduce a pre-trained frozen subject biometric classification network as shown in the upper right of figure. The loss function for the subject invariant component is used to penalize the generation of signals with subject-specific features, or the experimental evaluation. In this work, we use two datasets collected from non-overlapping subjects under two different conditions, which are offline datasets and online datasets. Both datasets are recorded using the same dry EEG headset with the same configurations. The offline data are collected on 9 inexperienced subjects with pre-recorded variable SSVEP stimuli. The online data are collected during real-time teleoperation application via real-time variable SSVEP stimuli on 3 subjects. The main results that can be found in this paper are 2 experiments on SSVEP classification for unseen subject to show the ability of the generated synthetic data in improving the generalization of the classification model given that there is no prior training on a particular subject. This table demonstrates the SSVEP classification for unseen subject experiments within the same offline dataset by leave one subject out at a time as a test set. The results show when the model is trained only on synthetic EEG signal generated by our SysGAN model and tested on real data, an accuracy level of up to 72.5% can be achieved, which is significantly higher than what a model trained on the same number of real data points can achieve. This set of results presents the SSVEP classification for unseen subject experiments on crossdust, meaning the training set is from offline dataset and we tested on totally new subject on online dataset. The result shows that training a classification model only with data generated using SysGAN outperforms a model trained on the same number of real data points. It is also of interest to observe that using the synthetic training data alone, SysGAN significantly outperforms ACGAN, highlighting the potential benefits associated with removing subject-specific features from EEG signals. We analyzed a subset of the generated data taken from a model trained on the offline dataset using a fast Fourier transform FFT. The FFT plots for the 3 SSVEP frequencies taken from SysGAN and ACGAN as well as the real data are presented in this figure. The figures show that when compared to the FFT taken from the real EEG signals, the generative model are capable of producing data which display the characteristic peak of the desired SSVEP frequency. This figure shows the data generated by both the ACGAN and SysGAN approaches are passed through the pre-trained subject network and the resulting softmax probability values are recorded. It can be seen that the data generated by C-scan has been assigned a low probability distributed across all 9 subjects, indicating that the subject biometric classification network is unable to find discriminative subject features in the data. As conclusion, our proposed approach demonstrates the efficacy of the synthetically generated data in improving the performance of downstream classification. By training only on synthetic data, the unseen subject generalization is improved when performing zero calibration classification. Thank you for your attention.